Bismillahirrahmanirrahim. In the name of Allah, the most beneficent and merciful. Dear student, Assalamu alaikum. Now we are back with our lecture number 3.6, which is the continuation of the previous lecture 3.5, in which we have discussed about the neutron diffractions. So this lecture is linked with the previous lecture. So I advise all of you to listen the previous lecture if you have not listened or not watched the previous lecture video. So before coming to this lecture, you must have the basic knowledge about neutron diffraction that we have covered in the previous lecture. So my name is Dr. Farhat Mahmood, and this is our chapter number 3 about single crystal X-ray diffraction, in which we are studying now the neutron diffraction technique. So in the previous lecture we have discussion about the planes of the molybdenum oxide, nickel oxide, and we also have discussed the comparison between the peaks taken by the X-ray diffraction and also by the neutron diffraction at a different temperature scale. So in the rock salt structure, the condition for reflection is that HKL, which are the Miller indices, should be either all odd or even. Hence, the first four lines to be expected in the powder pattern are 111, 200, 220, and 331. These are the peaks that comes out in the graph. So first four peak represent these planes in the pattern of 111, 200, 220, and 311. These are the Miller indices of the planes. All four lines that appear in both pattern, but 200 plane and 220 planes are weak in the neutron pattern B that was taken on different temperature. In the previous lecture, the small intensity of the plane 200 and 220 is in B is largely because the neutron scattering power of manganese and oxide are opposite in sign, although slightly different in magnitude. Partial cancellation therefore occurs for the plane 200 and the plane 220 reflections, since manganese and oxide ions on the same planes scatter out of phase with each other. This is precisely the opposite of the case with scattering of the X-rays, for which the scattering factors of all elements have the same sign, and therefore for the plane 200 and 220 reflection, manganese plus 2 and oxide scatter in phase with each other. The comparison of the above figure A and B shows that below Tn mean temperature, extra lines appear in the neutron diffraction pattern. These extra lines are associated with the antiferromagnetic superstructure. Although, as mentioned above, the true symmetry of the antiferromagnetic structure is rhombohedral, so to a first approximation, it can be treated as cubic with cell dimensions that are twice the value for the high temperature paramagnetic structure. That is, A is equal to 8.85 angstrom at 80 Kelvin. That is less than the Néel temperature, whereas at 293 Kelvin, which is greater than the Néel temperature, A is having a value of 4.43 angstrom. The volume of the unit cell are therefore in the ratio of 8 to 1. The extra line in the powder pattern of the antiferromagnetic structure may be indexed as shown. Observed reflections are those for which H, K, and L are odd. Note that because the unit cell for A is twice that for B, the reflections that are common to both have double indices in A compared to those in B. For example, reflection in the plane 200 in B has indices of the plane 400 in A. In this slide, we are going to study the inelastic scattering, soft modes, and phase transitions. So, when we use slow neutrons, these slow neutrons possess kinetic energy that is comparable to the thermal energy levels in the solid. Therefore, such neutrons are inelastically scattered by phonons, that is, vibrational modes in the solid. From an analysis of the energy of the scattering neutrons, information on phonons and interatomic forces is obtained, and for magnetic material, further information on their electron exchange energy is obtained. These are spectroscopic techniques using incoherent neutrons rather than diffraction techniques, which use coherently scattered neutrons. But these are mentioned here briefly for convenience. Dispulsive phase transitions are believed to be associated with the instability of lattice vibration. Certain type of vibrational mode, known as a soft mode, in the low temperature structure effectively collapses at the critical temperature. So the soft modes may be studied by IR and Raman spectroscopy, provided that the vibrations involved are spectroscopically active, and also by neutron scattering. The latter technique is useful since it is not limited by the spectroscopic selection rules. So by measuring the inelastic scattering about a number of Bragg's reflection, the atomic displacement that are responsible for the soft mode and the phase transition may be determined. For instance, the mechanism of the dyspelvic For instance, the mechanism of the dispelsive transition in quartz silicon dioxide at temperature 573 degrees centigrade has been analyzed by recording the neutron spectra at several temperatures below and above 573 degrees centigrade temperature. Here we comes with the instrumental and sample requirements. The technique requires a source of neutrons. So these neutrons are usually produced in a nuclear reactor or suppletion source. Other component needed, including a crystal monochromator as well as filters to select desired neutron wavelength. Some part of setup may be movable at spallation source. The time of flight technique is used to sort the energies of the incident neutrons. High temperature neutrons are faster, so no monochromator may be needed in some cases. The technique is most commonly performed as powder diffraction, which only require a polycrystalline powder. Single crystal work is also possible, but the crystal must be much larger than that are used in the single crystal X-ray crystallography. So it is common to use the crystals that are about 1 cubic millimeter. A beam can be used to perform a diffraction experiment and impinging on a crystal sample, it will scatter under a limited number of well-defined angles. According to the same Bragg law that is used to describe X-ray diffraction, neutron diffraction also takes place at well-defined angles. Diffractogram is obtained, a plot of graph of intensity and atomic number showing peaks of different intensities and angles. This plot is known as diffractogram. So here is some information that why neutron scattering is important. Neutron scattering is important because neutrons have no charge. It is highly penetrating. It is non-destructive technique. It can be used in extremes. Neutrons have a magnetic movement. It has a magnetic structure. It can have fluctuations. Magnetic materials can be used by using neutron scattering. Neutron have spin. It has polarized beam. It has atomic orientation and coherent and incoherent scattering. Neutron probe nuclei the light atom sensitive. It is also sensitive for the lighter atoms like hydrogen, and it is also sensitive to isotopic substitutions. That's why neutron scattering is important. So here is the process of neutron diffraction. Neutron diffraction occurs mainly due to two factors. One is nuclei in crystal, and the other factor is that the magnetic interaction between the atoms or the ions in the crystal and neutrons, and that between neutrons and unpaired electron in the crystal. In both the cases, the atom have magnetic moment or neutron scattering for the electrons. Here is some comparison between XRD versus neutron diffraction. In neutron diffraction, neighbors and isotopes can be discriminated, while in XRD, these neighboring atoms or neighbors and isotopes cannot be discriminated. While in neutron diffraction, light elements like hydrogen can be detected, whereas in XRD, such kind of light elements are hard to detect. And the magnetic structure can be investigated in the neutron diffraction, while in XRD, the magnetic properties cannot be investigated. In neutron diffraction, longer scan time is required, but in XRD, this time is shorter as compared to neutron diffraction. In neutron diffraction, there is a lower availability, where XRD has a higher availability. So here we are comparing electron diffraction technique versus neutron diffraction. In electron diffraction, the diffraction of electron is very common for investigating crystals, while in neutron diffraction, it is ideal to reveal structure of a crystal as well as magnetic structure of that crystal. The magnetic movement is one in electron diffraction, though not applicable for revealing the magnetic structure, while the magnetic movement in neutron diffraction is very small, that is 0.001, so it can reveal the magnetic structure easily. Electrons are strongly scattered by the atomic electrons in electron diffraction, while in neutron diffraction, as neutrons have no charge, so no electrostatic interaction occur with the atomic electron, and uh, electrostatic interaction dominates over the magnetic interaction in electron diffraction, while only weaker interaction with the magnetic moment of the atomic electrons occur in neutron diffraction. There are different modes in neutron scattering. One is the nuclear scattering. This kind of scattering involves the interaction of a neutron with a point like much smaller than the wavelength object. The nucleus So the scattering is isotropic. The other mode of scattering in neutron scattering is it involves the interaction of a neutron with the extended atomic electron distribution. So the form factor is more like that seen for X-ray diffraction, and it falls off quite rapidly with angle. The scattering which takes place due to the interaction between the magnetic moment of spin of the neutron and magnetic moment of the atoms. This scattering also takes place in the transition metal, mostly due to the presence of unpaired electrons. Magnetic scattering also associated with the electronic cloud around a tiny nucleus. The magnetic scattering length is comparable to the nuclear scattering length. This means that the magnetic and nuclear signals have comparable strengths. So here is nuclear neutron scattering, which are elastic neutron scattering. Diffractions can find out the crystal structure, and if the inelastic neutron scattering occurs, it can be used to find out the excitations and phonons. While in magnetic neutron scattering, if elastic neutron scattering occurs, that can be used for the diffraction and the spin structure, which is further used to find out the antiferromagnetic properties, magnetic moment, and direction of the spins. And if the inelastic neutron scattering occurs, then it can be used to find out the excitations of the atoms and magnons. The process of the neutron scattering. When the neutrons collide with the atoms in the sample material, they change directions, are scattered, and this is called mostly elastic scattering. So here we have a schematic diagram showing at the right of this slide there is a research reactor which produces these neutron beams, and these neutron beams are fallen on a crystal or the powder sample, which is after striking this sample are scattered at different angles and forms a diffraction pattern. After passing through the samples and after scattering from the atom present in that sample, these are then collected by the detectors, and then after collection the neutron diffraction pattern, different kind of softwares are used to determine the structure of a crystalline sample. Here is the basic model, which is showing the neutrons with different kind of energies coming from the reactor, and after striking the samples these are scattered at certain angle and their energies also change, and the change in energy can be taken as by the equations written on right side of this slide. So the momentum is equal to hk, where energy can be calculated by the h square k square over 2mn. Measure the number of the scattered neutron as a function of q and omega. The result is the scattering function, which is s function of q and omega, that depends only on the property of the sample. All we need to do is to prepare a neutron beam with wave vector k0 and measure the intensity of the neutron scattered with the wave vector k. In this slide, we are studying about the type of neutrons, which shows two type of scattering: elastic scattering. In elastic scattering, no energy transfer to or from the sample occurs. The crystal structure, atomic correlation in liquid and glass can be studied by using elastic scattering. While in inelastic scattering, energy transfers occur from or to sample. So measurements of the lattice vibration, phonons, and atomic diffusion and molecular modes are studied by using inelastic scattering. Elastic scattering changes direction but not the magnitude of the wave vector. While in inelastic scattering changes both direction and magnitude of the neutron. So dear student, this was all about our lecture number 3.6. Now we will come again with our next lecture 3.7. Thank you very much for listening this lecture. Till the next lecture, Allah Hafiz. See you again.